Points matter when designing nanoparticles that drive important chemical reactions using the power of light. Researchers at Rice University's Laboratory for Nanophotonics (LANP) have long known that a nanoparticle's shape affects how it interacts with light, and their latest study shows how shape affects a particle's ability to use light to catalyze important chemical reactions. In a comparative study, LANP graduate students Yuan and Minhan and their colleagues studied aluminum nanoparticles with identical optical properties but different shapes. The most rounded had 14 sides and 24 blunt points. Another was cube-shaped, with 6 sides and 8 90-degree corners. The third, which the team dubbed octopod, also had 6 sides, but each of its 8 corners ended in a pointed tip. All 3 varieties have the ability to capture energy from light and release it periodically in the form of super-energetic hot electrons that can speed up catalytic reactions. Yuan, a chemist in the research group of LANP director Naomi Hallers, conducted experiments to see how well each of the particles performed as photocatalysts for hydrogen dissociation reaction. The tests showed octopods had a 10 times higher reaction rate than the 14-sided nanocrystals and 5 times higher than the nanocubes. Octopods also had a lower apparent activation energy, about 45% lower than nanocubes and 49% lower than nanocrystals. The experiments demonstrated that sharper corners increased efficiencies, said Yuan, co-lead author of the study, which is published in the American Chemical Society journal ACS Nano. For the octopods, the angle of the corners is about 60 degrees, compared to 90 degrees for the cubes and more rounded points on the nanocrystals. So the smaller the angle, the greater the increase in reaction efficiencies. But how small the angle can be is limited by chemical synthesis. These are single crystals that prefer certain structures. You cannot make infinitely more sharpness. Liu, a physicist and study co-lead author in the research group of LANP's Peter Nordlander, verified the results of the catalytic experiments by developing a theoretical model of the hot electron energy transfer process between the light-activated aluminum. We input the wavelength of light and particle shape, Liu said. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.